The ACE tests with synthetic sounds consists of typical threshold measurement by means of an adaptive algorithm. The synthetic sounds are harmonic complexes, harmonic intonating sounds, and disharmonic intonating sounds. They are discrimination tasks to assess the temporal coding of sound. This video explains the rationale and is the same for the three tests. An harmonic complex consists of a fundamental frequency of, say, 200 Hz, plus its three harmonics at 400, 600 and 800 Hz. The intensity of each harmonic is 6 decibels lower than the former component. Such a sound would typically sound as follows. An harmonic complex of 220 Hz would have a fundamental frequency of 220 Hz and harmonics at 440, 660 and 880 Hz. It would sound like this. At each presentation, two sounds are given, one of which is always an harmonic complex of 200 Hz. The other sound is an harmonic complex with a fundamental frequency of 200 plus delta Hz, where delta varies between 0 and 214 Hz. The adaptive algorithm varies delta according to the listener's responses. It attempts to find the smallest delta that the listener is able to discriminate. This is called a just noticeable difference, or JND. As said, two sounds are presented, one of which is the harmonic complex of 200 Hz. The listener should respond equal or different. If the listener discriminates the sounds, delta becomes smaller, and vice versa. Internal controls and stochastic processes improve the test efficacy and accuracy. The graph shows the responses and how the algorithm converges to threshold. The cumulative responses for each delta can be followed on the histogram. The second test presents harmonic intonations. Again, two sounds are given, one of which is an harmonic complex of 200 Hz. This sounds like follows. The fundamental frequency of the second sound, however, starts at 200 Hz and sweeps to a frequency of 200 plus delta at the end of its presentation. The frequency of the harmonics sweep accordingly. This creates the perception of intonation. It sounds like follows. Again, the algorithm changes delta in an adaptive way and converges to find a threshold, or JND. Please notice that both with the harmonic complexes and the harmonic intonation, the cue to discriminate the sounds lies in the difference in fundamental frequency, together with the differences in the harmonics. Since phase locking is believed to be essential for the coding of low frequencies, ACE contains yet another type of synthetic sounds. These are the disharmonic intonating sounds. Again, two sounds are given, one of which is an harmonic complex of 200 Hz. The fundamental frequency of the second sound sweeps from 200 Hz to a frequency of 200 plus delta at the end of its presentation. However, the frequency of the harmonics does not sweep accordingly. This causes the perception of disharmony. Now the cue for discrimination is only contained in the low frequencies. Again, the algorithm changes delta in an adaptive way and converges to find a threshold, or JND. How to use and interpret the test results. since this test is fairly new. Its use and interpretation still have to be explored. It is believed that the absolute value of the JND gives an idea of the low-frequency coding of the cochlea. Preliminary data show that listeners with normal hearing have JNDs of less than 2 to 4 Hz on average, and of less than 10 Hz in most cases. This may be different in listeners with high-frequency or low-frequency sensorineural hearing loss, with hearing aids or cochlear implants. In addition, it is anticipated that within one subject, the difference between the JND with harmonic intonation and with disharmonic intonation is indicative of problems with the coding of temporal fine structure. Indeed, while harmonic intonation still contains high-frequency cues, disharmonic intonation does not. Bad coding of temporal fine structure may therefore result in a higher JND with disharmonic intonation, whereas the JND with harmonic intonation may remain better.